So there are a whole slew of objectives in this section. The reason that is because, quite frankly, the books I've used in the past don't do a great job of addressing some of the things that the AP test does address. So I kind of put them together into this super section to make sure that they get covered. The two that we're going to focus on in this particular video, though, are ironically the last couple, the ones I've gotten red here. We're going to use derivative values to determine if a left endpoint or right endpoint estimate for area under a curve will give an overestimate or an underestimate. I think we've talked a little bit about this in the past, but we're going to, I guess, formalize it today. And then we're going to use derivative values to determine if a tangent line approximation will give an under or an overestimate as well. If those don't make perfect sense to you, we'll draw some pictures to start off and kind of get maybe a little better visualization of what's going on. So simply wants us to sketch a continuous function that meets each pair of conditions. First derivative is positive, second derivative is positive. First derivative being positive means the graph is increasing. Second derivative is positive means the graph is concave up, like a cup. So those two things working in tandem would give us something like that. Next example, first derivative is positive, second derivative is negative, so we still want an increasing graph that's opening down like a frown. So increasing but opening down would be something like that. Over here we have first derivative is negative, second derivative is positive. So we want something that is decreasing but is opening up like a cup. So decreasing and opening up would be something like that. And finally, first derivative is negative, second derivative is negative, something that is decreasing and opening down like a frown. Something like that. Then it asks us below each graph to write down whether a tangent line approximation would yield an under or an overestimate. So if you just draw in a tangent line in each of these situations, you can see that you'd have an underestimate here, an overestimate here. The tangent line is under the curve here and over the curve here. So this would be underestimate, overestimate, underestimate, overestimate. Then it also wants us below each graph to write down whether a left endpoint approximation for area would yield an under or an overestimate. So if I drew in a lefty rectangle, this would yield an underestimate for the actual area. There'd be some leftover unaccounted for space above the rectangle. If I drew in a lefty here, I'd also be under. There's a little extra space above the rectangle, but still below the curve. Whereas here, I would have an overestimate because I'm including some space that's not actually under the curve. And same deal here, if I drew in a lefty, I'd be including some space that's above the curve. So that would be an over as well. Alright, so to summarize what we've got here, a tangent line approximation for a function will be, let's see, we are under in these two situations, and in both of these two situations, the second derivative is positive. So the tangent line approximation will be less than the actual value if f is concave up. Or put another way, if f double prime at c is greater than 0. So if the second derivative is positive at the point of tangent c, you're going to get an underestimate for using the tangent line. Obviously this would be vice versa. This would be greater than if f was concave down. Following up with that, a left endpoint approximation for the area under a curve. So these are all left endpoints. We are under here and we are under here. In both of these cases, the first derivative is positive. So the approximation will be less than the actual value for the area under the curve if f is increasing. on the interval. Or to put it another way, if f prime is positive on a to b. And vice versa if you'd use a right endpoint approximation. So the last question on that side says, if you change the tangent line situation to a secant line, would there be a change in the conclusion? So if I've got, here's my curve, I've got now, instead of a tangent line, which would be an overestimate in this case, what if I drew a secant line? Secant line intersects a curve in two places. Would the conclusion be the same? Would you still have, in this case, an overestimate? And I guess the answer is probably. If C is outside the interval formed by the points of intersection. So if the place you're trying to estimate is outside the window, the domain where the curve intersects the line, then you're still going to play by the same rules that the tangent line played by. On the back we have a couple examples in the form of old AP problems. So here's a problem where we are given certain values for a function of x. We know that x is twice differentiable, which means that its second derivative exists everywhere. And we also are told one little piece of information about its first derivative, and then we're told that its second derivative is negative on this very narrow window from 5 to 8. They want us to do a bunch of things, including, use the tangent line equation at x equals 5. That's why I've got this box circled here, because that is the point of tangent C. We want to show that f of 7 can't be any more than 4, a height of 4. And we'll do some other stuff after that. So one way to do this is just to actually literally write the slope-intercept equation for the tangent line. The point of tangent C is 5, negative 2. So I'm going to use negative 2 for my y value. I don't have the slope from this table, but I guess I got it here. This is going to be my slope at that point. Slope is 3. The x value in question is 5, and that'll yield us a b value of negative 17. So we get y equals 3x minus 17 for the tangent line. By plugging in 7 into this equation, 3 times 7 minus 17, we get 21 minus 17, which is 4. So we've gotten the same number that they're proposing here, 4. The question becomes, how do we know that that's the very highest value it could possibly be? And that's a little bit the tricky part. But if you go back to what we were just talking about on the previous page, notice they're telling us the second derivative is negative. Well, anytime you have a negative second derivative, your tangent line approximation here and here, the second derivative is negative. The tangent line approximation is actually more than the actual value of the graph. And that's what we've got going on. This 4 that we're coming up with is more, or possibly equal to, but most likely more than the actual value of f of 7. So our justification here can simply be, since f double prime of x is negative on 5 to 8, 4 is the greatest possible value of f of 7. And we've already done the work to show that 4 is the number that we'd end up with.